Quantum entanglement, if I described it to you and didn't tell you it was called quantum entanglement, you'd think I'm talking about voodoo. I put a pin in a doll here, and some friend of yours on the other side of the city feels a pain, and you think like,
is this where there's like, forgive me if I'm wrong again, but particles on different sides of our universe that are sort of like they're in sync with each other since the beginning or something like that.
Yeah, absolutely.
Electrons
and
or something.
Imagine if voodoo, imagine if I said, turns out that's true, and scientists have managed to figure out how to exploit it and use it. What would you think? You'd think, all right, I'm going to go and stick some pins in people. But then you probably think, I should be able to build a technology, but what's that good for?
Yeah.
We don't know.
Yeah.
We don't know what it's good for yet.
We don't know.
But
because the technology is only as good as the ideas that are.
That's right.
It's being used for, really. It still depends on us.
All right, lads, before we start today's yarn, I want to shout out Manscaped. They're supporting today's episode of The Search. They've launched a new product, the Lawnmower 4.0, right? It's the best clipper for shaving down there. Legit, it's the best clipper. You know all them other clippers, they cut you, they graze you, this and that. It's the best clipper, and I got a code for you. If you go to manscaped.com, you get 20% off by using the code TheSearch. You can click the link in the description, it'll be there, or go to manscaped.com. Make sure you use the code TheSearch, you get 20% off. Gun clipper, lad, go check it out. Hey,
All right, welcome back to The Search, everyone. Today's guest has been described as a rock star scientist. He's a quantum physicist with a degree from Harvard who works as the director of a state-of-the-art $150 million nanoscience lab trying to invent the quantum computer. Damn. If all of that sounds like googly blook gook, as it's written here, I don't know what the hell that... If all of that sounds like rubbish to you, and don't worry, we'll get to the bottom of it. But this man right here is the guy to explain it to us and help us understand why quantum computing is going to change the world and define what our future looks like. Welcome to The Search, Professor David Reilly. How are you, brother?
Very well. Thanks for having me.
Start at the beginning, brother. You grew up in Sydney, and more specifically, Matto.
I
grew up in Matraville, 2036, brother.
Exactly.
How did it come about that you got like... So what do you do now? You're teaching...
As you said, I grew up in Matraville, local school. Didn't do particularly well in school. Okay. Got through.
What school did you go to?
I went to Soldier Settlement Primary School, and then I went to South Sydney High in Maroubra.
Where's Soldier Settlement?
Yeah, it's right in the heart of Matraville.
Is it? Yeah. And you went to South Sydney High?
Yeah, went to South Sydney High.
And you always liked science there?
I did. I didn't know what physics was.
Yeah.
I like pulling things apart, building things. I'd pull radios and torches apart and hook wires up to the gutter of the house, that kind of stuff.
Yeah.
I didn't know that was physics. Some people would call it engineering. I think engineering's really focused about building something.
Yeah.
This was trying to understand it, trying to figure it out. How does it work? What's the underlying principles?
Yeah.
I was also interested in those sort of bigger ideas, the philosophical stuff that we're talking about. Physics is that intersection of the technical, the mathematical, but also there are philosophical ideas, big picture stuff. I didn't know it was called physics, and I ended up going to university, and at the time...
you went to Sydney Uni?
I went to
you went to Harvard?
I started off, I went to UTS, and I showed up, and as I said, I didn't do particularly well at school, and I was scared. The first math class there, the guy said, all right, we're going to cover all 4-unit maths. This is back in the old system, in the first 2 weeks. So I thought, I didn't do 4-unit maths. I didn't do 3-unit maths. What am I going to do? So I just studied like mad. And first exam came, and I blitzed it. And I thought, it's easy.
Yeah.
After that, I failed.
That's it.
Then I picked it back up later on, but it was
the maths is the part that I hated. That's what turned me off the physics books I used to read. So when I was in jail, you probably read it in my book. When I was at Bathurst, I used to read like physics books. I think they were university first year physics books, and I loved it all. I loved it all. I loved chemistry and like understanding matter and energy and stuff like that. I loved it all, and I don't know, I really loved light and the hurt rate of light is different colors and stuff like that. Until it got to kinetics. And I thought, fuck this, bro. The movement, the momentum, and to calculate this. And if I chuck a football here, use mathematics to tell me where it's going to land. I was like, fuck this. So when I got into that stuff, I was like, hopefully there's computers that do that now, and you aren't sitting there doing maths.
It's crazy the way we teach. It turns people off like that. Yes, you need that stuff. You need it at a certain level, but I don't know why it comes first.
Yeah,
so now I have 2 jobs. I work for University of Sydney as a professor of physics. So I've been doing that for 10 years, a decade of teaching lectures in physics and classes, running a research group. So really trying to advance new technologies, thinking about what might be on the horizon in a decade from now, 20 years from now, trying to understand, new directions. But let's see, 5 years ago, I actually transitioned to also having a major role within Microsoft that's also interested in the frontier, obviously, of computing and what's possible with the latest technology. So I got 2 roles there, and my life is pretty hectic, trying to sort of balance both of these, but keeps me busy.
That sounds crazy.
Yeah.
So the types of physics that you're teaching, right? So I have a little bit of understanding of physics. But you're not sitting in a class teaching people about matter and energy.
I have done.
You have.
Yeah.
This is what kids are learning in Year 10, though.
Yeah.
Yep.
And it's the same concepts that you hear about in high school or even earlier. It's funny. High school physics, I kind of liked it, but I wasn't that good at it, and it was a lot of inclined planes and rolling balls and energy and all this stuff, and and look, that is a part of physics, but modern physics and the kind of physics that I'm involved with in terms of the research I do, much closer to other creative things like music or art, or wake up in the morning, think of an idea, think of how am I going to solve a problem? How does something that is not known become known, and how am I going to get at that? That's not sitting down doing problem sets. That's thinking in a very different way, grappling with ideas, concepts, walking around, just going for a long walk, trying to figure it out, a solution, and invent something that doesn't exist. That's a lot of what modern physics
theoretical
is.
Physics like that. It's mostly, it's not numbers. It's mostly in the mind.
Absolutely. I'm what you'd call
creativity.
An experimentalist. So I build things, I wire things up and put things together. One part motor mechanic, one part mathematician. And so...
Give us an example of stuff that you're working on now.
Yeah, I mean, we're really trying to realize technologies that you won't see for many years. Maybe a decade, maybe 2 decades or beyond. What is the limit of computability? What does it mean to we think of this technology we have today, we all carry it around in our pocket, and we connect to the NBN or whatever. But then when you're scrolling,
sometimes we connect to the NBN. Sometimes,
when you're scrolling on Instagram and you push past photo after photo, most people don't think what's actually happening there in the cloud. Somewhere out there in a data center, there are racks of machines and a huge amount of technology and energy that is getting expended to make that happen. Our thirst for more and more computing power, not just for entertainment purposes, but in solving big challenges for society, come down to computing power. And yet, on the path that we're on, we're running out of opportunity to build faster computers, better computers. There are limitations. You can't just keep making it smaller and put more transistors on a die and increase the clock speed. I mean, if you go and buy a computer today, the clock speed is approximately what it was last year, approximately what it was the year before. It's increasing maybe a little bit, but we're adding more and more processors, looking at other ways of building power there. But we've plateaued. And it's flatlined.
So it needs just a completely redo.
Exactly. And the crazy thing is, and the thing that really just drives me is the realization that there is a regime that you can get to, a way of computing that at the moment we don't touch. We don't exploit it. We don't tap it. There is a different kind of physics based on quantum physics. We should talk what that is. A different kind of mathematics that at the moment is untouched by our technology.
Really?
We want to grab that. What can we do with that?
So this is quantum computing.
This is quantum computing.
Is it so? Forgive me if I sound completely stupid numerous times this podcast. All right,
not at all.
So does this not run on the binary system that the other computers run on?
Right, exactly. So computers that we have today are digital. There are other ways of computing. And when you think of, well, I don't even know what computation is. Think of something like crazy idea. Imagine you go to the beach and you look at a wave coming in on the shoreline. Hits the shore, bounces off. Many people have seen this before. Two waves collide. If they collide in phase, meaning that the peak of one wave and the peak of another wave hit at the same time, you end up with a wave that's twice as big. Addition, it added this wave and the amplitude of this wave together. If a peak and a trough come together, they cancel one another out and there's calm. So waves colliding are actually adding, they're adding their amplitude, adding their energy. Nature computes for us in its behavior. Imagine you now encoded somehow information in the wave state and you said, well, I've got to add two numbers. So I'll make a wave of a certain amplitude, 3 units, and another wave of a certain amplitude, 5 units, and I'll collide them. And I'll measure the resultant, and that's 8 units. Well, okay, nature did the computation for you. And even though we think of computing as digital binary representation of numbers, under it all, we're exploiting some physics, in that case the physics of waves and how they add up, to arrive at the answer of a computation.
Really?
So
I'm following you.
That
sounds mental to most people.
Yeah,
I've never heard that before. I'm following you.
It's under it. It's a physical phenomena. It's you're using some law of nature. And nature's computing. When you step back and think, well, if two waves overlapping at the beach are computing. Like as I look around, the light bouncing off the table. Nature is computing itself continuously. It's just we're not encoding information or accessing that. A computer, it's underneath it. It's something that is, of course, manipulating information based on physics, and that, as you said, that binary digital representation. Turns out, the history of that is that it was developed to reject noise by encoding information in a 1 or a 0. If it's a 0 plus a bit of extra noise, it's still a 0. If it's a 1 plus a bit of noise, it's still a 1, and I can distinguish the 0 from a 1. So that encoding mechanism is very robust to noise. But there are other ways to compute. You can compute with waves, for instance, and that's called analog computing. The Apollo mission that went to the moon.
Has things already used analog computing?
Exactly, yeah. So if you go back to the 60s, the space race, analog computing was very powerful. It wasn't until many years later, through the late 70s and 80s, digital computing took off because we could make a lot of transistors. Turns out that way of doing things, even though it's robust to noise, it requires billions of transistors. It's actually really inefficient. But the point is, there are other ways of computing, and the digital representation has its limitations. And we're hitting up against those limitations today. We're starting to run out of room on what we can do. We're looking for new ways of computing.
And so leading that is quantum computing, hopefully.
Well, it's quantum computing is a totally different way of doing it entirely.
Did you describe it within all of that?
So let's go back to let me tell you where a lot of these ideas came from. It's crazy. There was a PhD student who was not a good student back in France in the 1920s.
It's funny how people that weren't great students done all of these memorable things.
I was not a good student at all, and
the story of everyone that's memorable. It's like he was in school and he wasn't that great, and the teachers hated him, but he changed the world.
It's often the way it goes. So this guy was not a good student. He would come in and go to sleep. Come in around about noon, take a nap. It was his first thing, and then wake up, go home. And his supervisor at the time said, got to get rid of this guy. So there's a way of moving people on. You say, it's time to write a thesis. And you've got, a month or so to produce something. And by the way, your thesis is going to be examined. It's going to be marked by Einstein. So the poor guy, his name was Reilly, and he thought, what am I going to do? It's going to be marked by Einstein. All right. What's Einstein done? I'll read about that. So, he was familiar with Einstein's work. And Einstein at the time, it's gone back 100 years now, Einstein had recognized that light had these two different personalities. Light, what is it? It's weird to think about. Well, sometimes it behaves a bit like a wave. We're talking about waves at the beach. Light looks like a wave. It can overlap and create these effects that we call superposition, that is waves overlapping in space.
Yep.
But sometimes light also behaves like a particle, like a clump of something, like I flick it at you, and like a...
Is that a photon?
Yeah, exactly. And we would call that a photon,
Yep.
a clump of energy.
Yep.
As to whether it looks like a wave or whether it looks like a photon, a particle, well, that depends.
Yeah.
It depends on what the experiment is or how you measure it, how you look at it.
I've
So it's
seen
got
some
these-
freaky stuff with light about how they've done those slits and
Exactly,
light, and
yeah.
things were in multiple places at the same time, and it's related to this type of stuff.
I
Some mind-blowing stuff with light particles.
Absolutely, yeah, crazy. So this 100 years ago was all the rage. Light, is it a particle? Is it a wave?
Yeah.
Well, it's actually something that's our language. That's human language to describe something about nature, but it's neither and it's both. It's an entity that is something else.
Yeah.
Sometimes it looks like one or the other. Okay. So back to this guy de Broglie in France. He's given, you got to write a thesis.
Yep.
He thinks, well, light. Einstein's shown that light can be a wave and a particle. What about this stuff?
Yep.
What are we made out of? Particles. And you go, well, I'm going to take a guess and punt on the symmetry of nature. Maybe matter, which we normally think of as particles, maybe matter can also be a wave. What the hell does that mean? Doesn't make any sense. Okay, 2 years later, experimental evidence showing indeed matter, atoms, electrons, the stuff that we're built out of, behaves like a wave. Nobel Prize in Physics.
Really?
So,
and they were trying to set him up.
Exactly.
They were trying to set him up, and he comes out with that.
Yeah, but he pulled it out of nowhere.
What was his name again?
De Broglie was his
de
name.
Broglie, yeah.
And his hypothesis or his suggestion, which was an appeal to the symmetry of nature, was that there would be a wave-like character to matter, which is so mind-bending for us because we don't, all our intuition is about, in the world we live in, what physicists would call a macroscopic world.
Yeah.
The laws of nature at the nanoscale, a billionth of a meter, at the level of atoms, vastly different. Crazy. And quantum physics is the physics of waves. Quantum computing is actually computing using the waves of fundamental particles like electrons and encoding information, just like what we're talking about, the waves at the beach. But this time it's going to be the waves of the atom and waves of electrons overlapping. Let me make it simple. It's
Please.
Imagine you're looking for the right answer.
Yeah.
I'm trying to compute something. I can't find the answer. Maybe the answer is, where did I leave my car keys or something? Well, okay, you could think about all the wrong answers. Where aren't your keys? They're not in the bedroom. They're not in the lounge room. A good algorithm of a quantum computer sets up the problem such that the right answer, the answer you're looking for, emerges from what we call constructive interference, the overlap of those waves to create a big wave, the correct answer, and all the wrong answers are going to cancel one another out. That's like a peak and a trough coming together, cancel one another out. So you're actually encoding information in waves, allowing all of those waves to overlap effectively so that the right answer emerges and all the wrong possible other answers cancel one another out. Sounds nonsense.
It's crazy. It's a lot to take in. It's
a lot to take in.
Definitely.
Yet 10 years from now, 20 years from now, being able to manipulate the world at the level of atoms and electrons, code information and even compute, will open up the possibility of doing entirely new things.
Yeah, see, I want to ask that. Right now, with the way we're doing it in the digital system of like computing, central process, CPUs and that, what do you feel like, so we're approaching the limitations of it. How much do you think that we have left in it? Say, for example, we never understand quantum computing, right?
And we might not.
And we might not. What are the limitations of it, and what are the issues involved? Like, why for you, for example, do you have a vested interest in furthering computers? Like, what, you know what I mean? Like, are we facing some issues now in advancements?
For sure. And the companies, the industries that push on this, it's big industry, a lot of money. They're very clever, and you'll see, I think, a lot of improvements in computing by just refining and furthering the engineering, moving to different material systems, different geometries, different architectures. But all of that is still constrained by the basic technology is transistors,
Yeah.
switches. They're either on or off,
Yeah.
and at the end of the day, that's going to be a limitation of what you can compute.
Yeah.
Even if you make it super fast and super efficient, and there are some problems that are even beyond what you can compute. And the computer might run for the age of the universe.
Yeah.
You're still not going to get the answer. Some problems, not all problems, but there are a class of problem that a quantum computer could solve efficiently that you'll never be able to solve with a digital classical computer.
Just because of speed?
Just because of the way in which it's computing.
All right. Yeah.
So, a good example would be...
so is it efficiency or speed?
It's really...
Is
I mean,
that
it's
not a way to
both.
ask
It's
it?
No,
Yeah.
it's kind of both, but
kind of
it's
both,
more that... efficiency is probably a good way of...
Yep.
Yeah. What resources would it take? So a good example would be... and to bring it to something practical, like imagine you're trying to design a drug or a pharmaceutical treatment for cancer or something like that. Drug design or materials design, well, what is that? Well, that's actually about molecules and atoms and electrons. And that's big money and big industry to design drugs to target particular diseases. Some of those challenges, not all, but some of them turn out to be really hard to design what the molecule should look like. And if you were right now to go around the world and say, give me a list of the top supercomputers, what are they running right now? Well, some of them are running, things for governments. A lot of them are running quantum chemistry problems and trying to actually solve chemical problems related to, say, drug design, for instance. It's a hard computational problem that requires supercomputers to run for a very long time because, and this is to your point of efficiency, digital classical computers absolutely suck at trying to capture quantum physics of molecules and atoms and electrons. If you build the computer out of quantum physics, that computer is really good at computing quantum physics problems, which are the problems of drug design. So
how would this look? So I'm imagining, so there's our CPUs right now, like they look like motherboards, whatever they are, you know what I mean? I'm imagining this quantum computer to be this crystal ball of glowing purple energy. Is that what it would look like? What would they look like if what casing is needed? Because if this is like manipulating things on that level, does it look like what we're normal to look like?
Yeah, great question. Yeah. It depends on the particular flavor of quantum computer. So at the moment, we haven't narrowed down the search to a particular type of even technology. At the moment, there's a race worldwide. So it's a little bit like computers back in the 1930s and 1940s.
And you're part of this race.
Absolutely, yeah. That's my everyday. Is it going to look like before the invention of transistors, people had various different systems that they thought might be used to build a computer. So it could look very similar to a silicon CPU. It could. It also might look very different to that. It might look like something that's encased in stainless steel and laser light and vacuum and those types of things. Underneath it all, both of those approaches are trying to manipulate single atoms and electrons and photons and encode information in the state of those fundamental particles.
Does your mind ever, obviously, what does your mind think about when we reach that technology? Is that like a super definitive point in mankind? Does everything just explode after that?
Yeah, it's a great question. I don't think anyone really knows. Part of the thing that just both motivates me but freaks me out as well as the physics here, we haven't yet really tapped that or exploited it. And some of that physics is absolutely nuts. So, give you an example. Probably the most counterintuitive thing I know of, something called quantum entanglement. Quantum entanglement, if I described it to you and didn't tell you it was called quantum entanglement, you'd think I'm talking about voodoo. I put a pin in a doll here and some friend of yours on the other side of the city feels a pain. And you think
is this where there's like, forgive me if I'm wrong again, but particles on different sides of our universe that are sort of like they're in sync with each other since the beginning or something like that.
Yeah, absolutely.
Electrons
and
or something.
Imagine if voodoo, imagine if I said, turns out that's true and scientists have managed to figure out how to exploit it and use it. What would you think? You'd think, all right, I'm going to go and stick some pins in people.
Yeah,
but then you probably think, I should be able to build a technology, but what's that good for?
Yeah.
We don't know.
Yeah.
We don't know what it's good for yet.
We don't know.
But
because the technology is only as good as the ideas that are
that's right.
it's being used for, really.
Yeah,
so it still depends on us.
Yeah.
Jesus. So this is what you're doing. You work at what's your lab at Sydney Uni?
Yeah, so we have a major lab there on the campus of the University of Sydney, in a building that was created and designed for quantum physics.
Yep.
Turns out, if you want to do these types of experiments, not so easy to do in your lounge room or in your backyard. Get
$150 million lab,
$150 million building that was created to enable quantum physics. Yeah, the University
what's
of
it called
Sydney.
again?
It's called the Sydney Nanoscience Hub is the building, and then we have Microsoft Quantum Sydney lives within that building.
What's your worries with stuff like this, bro? Like, as forgive me, bro. Like, obviously, a big lack of understanding, but do you ever get drawn into the conversations about the worries of extreme technologies like that?
For sure, and this is one where if you look at the world today and the geopolitics of the world, which country is going to hold this technology first? And what are they going to use it for? One of the, if not the defining most important application that started the field, at least really accelerated the field, was breaking codes. Turns out if you could build a very large quantum computer, this hasn't been done yet, but if you could, then the means of encrypting data that we rely on for everything that we do these days, that approach becomes vulnerable to a quantum computer.
Oh, of course.
So whoever holds that technology, that's pretty enabling.
So it's that's like the master key.
Exactly.
It just cracks everything. It's too powerful. Yeah.
So now, having said that, there are ways of potentially encoding information that would resist a quantum computer, and that's an active area of research. How do you develop means of encrypting data that would still be resistant to such a machine? But that doesn't help you if the last 30, 40, 50 years in the vault you've been doing it the other way. Imagine all those secrets are suddenly exposed.
Imagine, what happens? Imagine gaming on a quantum computer. Imagine gaming, brother. Imagine the GPU you'd be using.
Exactly. Imagine different rules of the game because of what's possible according to quantum physics.
So with a powerful quantum, like just going full theoretical here, you could legitimately run simulations. You could. It would be powerful enough to run simulations, fully realistic simulations.
Exactly. Of certain types of things. I mean, a quantum computer won't do everything. A lot of people you read in newspapers sometimes as if it's going to make every problem that was ever hard suddenly easy. And that's not true. There are some problems that are beyond classical computers that we have today and will always be beyond them. Never possible a quantum computer can solve. But there are still problems that are beyond quantum computing. And the world has to be that way. It can't be that everything suddenly becomes easier. It just it doesn't make sense.
We'll never be gods.
Exactly.
We'll never be gods. Yeah. Let me ask you about, related to that simulation, brother. Let me ask you some personal beliefs.
Yes.
Since you're in that world.
Yeah.
What do you think is, in your mind, what's the possibility that we live in a simulation?
Yeah, great question.
Yeah. And what type of things, knowing that field you work in, if you were to look at our world and guess if we're in a simulation, would you be looking for? What type of patterns exist that you can see that do exist?
Yeah, it's a great question. I mean, you're crossing in, I should sort of say, you're crossing into metaphysics, philosophy, of which I'm really curious about, but you're starting to push out of my area of expertise.
Yeah, of course.
So, I mean, as someone who kind of works within the field, I would say... going right back to what we started with, the idea that we're talking about waves overlapping and all that stuff, and the idea that those waves are doing addition when they collide, and you start to think that everything in the world, well, what's it computing? It's computing itself.
I actually thought of that when you said it. Yeah. When you said essentially what our processes are doing, nature is computing itself, and I was thinking, wait, there's people that say this.
Think of a problem, a physics problem from like, I don't know, high school or something. I'll throw a ball through the air and you've got to compute where it's going to land. Here's its initial speed and its angle, and you can figure out the equations to use and whatever else. Or you could throw the ball and see where it lands. The ball did the physics problem for you. How did it do that? Well, it's computing its own trajectory. In some ways, every atom, every aspect of the world is the universe is computing itself, its own evolution in time.
I find that so interesting. Especially like when people were arguing about the amount of rendering that would be needed is unrealistic. But then people saying it's only when you face something does it activate, in a sense, and it renders only when it's being observed. And that relates right back to that photon. That is, wherever you observe it to be, it's there. But if you observe it to be there, it was there at the same time. And I love how all of that stuff's really interrelated.
That's a principle, a very fundamental principle of quantum mechanics, is this perspective that when you measure something or you observe it or you look at it, then the act of observing it affects it. It takes something that is could be any possibility and turns that any possibility into some particular outcome. That tree falling in a forest, if no one's there to hear it. I mean, this is reality. I mean, this sounds crazy. My everyday world is doing experiments, 500, 600 meters from where we're sitting, effectively.
It's down the street.
We're doing experiments to test those ideas and then go beyond just testing them, start to think about building technology to do things that we can't do today.
Tell me some
based on
stuff you
those
actually
laws.
get up to in there. $150 million lab, working for Microsoft.
Exactly.
I imagine it to be like Men in Black. You walk in, there's aliens everywhere.
It's pretty relaxed. It's pretty relaxed. But
what do you do?
We have a lot of equipment, purpose-built equipment, as well as we have equipment like refrigerators. Sounds pretty mundane. It's not going to be your white good from Harvey Norman. These are refrigerators that get to a temperature a fraction above absolute zero. Absolute zero is minus 273
Kelvin zero?
Kelvin,
Kelvin
exactly.
Zero,
So really close to that temperature where all thermal motion stops. When you feel something's hot, it's jostling around. It's all the atoms are vibrating. And if you cool things down, those vibrations slow and slow and slow, and at zero they completely stop. Now, we need to look at quantum physics phenomena that's very weak, and if everything is jostling around like it is at room temperature, you'd never see that fragile quantum physics. So we've got to get the thermal energy at the lowest temperature. So we have fridges that do that. The way they work, they actually exploit helium, not your regular balloon gas, but something called helium-3, which is an isotope of helium. It's regular old helium. It's missing a neutron. Helium-3, where does it come from? Well, it doesn't occur naturally on the Earth. You can get it from the moon. You can go and mine the moon for helium-3. It's full of helium-3 from the sun. But helium-3 on Earth comes from the decay of nuclear weapons. Really? So it's the only peaceful application that I know of nuclear weapons sitting there in a stockpile, aging. And as they age, the elements that are in those weapons, plutonium, uranium-238, they decay into other elements. They're unstable, really? And as they decay,
so it's not the fission process of the uranium. Is it?
It's a process of nuclei that are unstable, just breaking apart effectively, emitting particles as they do that. And as they break apart into simpler other elements.
Really,
and when there's a whole chain of processes where these big heavy atoms that make up weapons start to decay down into more stable elements. When they do that, there's a process that gives off helium-3, and that's collected. They collect that gas and then sell it back to us.
So these sorry, let me get into chemistry a bit here. I'm genuinely interested. So these more elements break down. As they break down, so what are they doing? They're giving off electrons.
They can give off electrons, sometimes photons of energy.
And as they give those off, they're turning into different elements.
That's right. Yeah.
Because I remember that's what the periodic chart is that's the number, and the number is the amount of of electrons that it holds on
number
to.
Of protons or number of electrons, and the number of neutrons. Yeah.
Right.
Yeah. And so each element.
So uranium's high up, right? Was it 236 or
those
lines?
Depending on...
I'm flexing here.
You sure are. There's ones that are not stable, so you can push more and more neutrons into the nucleus or protons, and you can change how stable it is. So if you want to make a fission, weapon, then it's going to be something that's on the edge of being stable and can be easily split. It gives off a lot of energy when it does that. But if you just leave the thing sit over time, slowly... It will decay. It'll do it itself effectively, and eventually you'll end up with lead.
Yeah.
But that'll take a long time as it decays
It will
down.
eventually end up in lead.
As
So that's
lead,
the most
it'll just
basic
turn
of
to
basic.
it'll just decay down to lead.
Yeah.
But yeah, it gives off helium-3.
Yep.
We collect that. We don't. The US government
Yeah,
does.
yeah.
They sell it to us. It's very expensive, many thousands of dollars a litre of gas.
Really, yeah.
And it turns out with helium-3, you can condense it and form a liquid and actually get to temperatures a fraction above absolute zero.
Yeah.
So we have, 7, 8, 9 of these fridges that have this helium-3 in them, and we use that to cool tiny electronic circuits that are a billionth of a metre in their size.
Yep.
And that's where quantum physics starts to rear its head.
Yeah.
So we've got to get to that extreme of nature. Very small, very cold, and a lot of the measurements we do or experiments we do are very fast.
And it's observable on a screen?
Eventually,
printout?
that's right.
Yeah.
Yeah. It used to be printouts maybe 30 years ago. These days, you're staring at computer screens that are capturing data and trying to interpret that data. What is it telling you about the thing you're actually building and measuring?
How does this does anything they do at the Hadron Collider over in Europe relate to this?
Yeah, that's particle physics. It's kind of loosely related in that all of these areas of physics are progressing our broad understanding. Particle physics is probably a little bit more fundamental in trying to test the theories of how the fundamental particles work.
So the fabric that we exist on, really, as opposed to...
Absolutely. As opposed to maybe trying to build a technology out of it, but closely related.
Yeah. Essentially, let's talk about AI.
Yeah.
It's a big interest of them. And would that be heavily reliant on the stuff that you do?
It's a big area of interface. No one knows. I mean, this is the crazy thing. A lot of people think, physics today, everything must be known. Yeah. We're just living out in the end times but nothing is further from the truth. So much is not known. We don't yet know what happens if you have a quantum computer. Can you do some kind of quantum AI? Does that even make sense?
Because to me, in my head, when you're saying that we're reaching the limitations of what we can do with this technology, and there's future and we could do so much more stuff that can think well beyond us and solve problems that we can't solve. Yeah. All of this sounds like, well, really, we can't really have AI until we think of some new type of computing system. And once we do, boom.
It's very interesting.
How do you feel about AI? I don't need to say to you, you can imagine how many people you already know have questioned your AI, it's so dangerous, this and that. What is your, because obviously your mind I'm not saying you're sitting there working on AI, you're working on a technology which one day may lead to it, but you must have some type of opinion on it. Is it as scary to you as it is to most people?
It is.
Yeah.
And it's scary to watch people who are deeply in that area, pioneering new approaches and ask them the question. And I think that broadly within these companies, there is deep appreciation for the need for ethical systems and structures around the way that whole world works, and Microsoft, for instance, is not going to sell you technology without knowing the application there and being deeply mindful about its ethical use. 100%. We need scholars. We need people thinking deeply about the human side. What are the implications of these technologies that we're building? This is new territory, and we're out into
like
crazy
let me give
world.
You a comical scene, bro. Have you seen Terminator?
Absolutely.
Do you ever feel like you could be, Skynet? Do you ever feel like, without knowing it, you're like the bloke now that's doing the things, and in the future when there's robots running around, everyone's like hunting you. You're the bloke. Like imagine like you make the discovery in the quantum things, and now us, John Connor comes back to find you. And
it's crazy.
They send the Terminators after you, bro.
Yeah.
Sorry, Ron.
But it's true. We're living in our lifetime. We are going to see a huge transformation. It's just accelerating. Where will we be in 20 years, and what's changed? It's very scary.
100%.
Exciting, but scary.
Let me ask you stuff off that topic, brother. Aliens.
Yeah.
Because this is science-related stuff, brother.
It is.
You believe in aliens?
Yeah, it'd be hard to... I would be very skeptical of anybody that said categorically no.
No, 100%.
I think the most interesting question there, though, is a question that usually goes by the name of the Fermi paradox. So Enrico Fermi in 1950, famous physicist, nuclear physicist, over a lunchtime discussion with his other colleagues, they were trying to estimate what are the chances of intelligent life elsewhere in the universe. Well, how many stars are there? How many galaxies are there? How many Earth-like planets are there, which we can now detect? We have the ability that they didn't have in 1950 to know that there are Earth-like planets. What's the likelihood of life developing? What's the likelihood of intelligent life? And then a big one, what's the likelihood that life form survives long enough, doesn't blow itself up, in order to develop technology that you can use to explore the stars? And so you put numbers on that.
So all of those, what are those numbers?
Exactly.
Is this the equation of Frank
Drake?
Frank Drake equation. Yeah.
So if you think about that Drake equation and put some rough numbers on it, apparently the story goes that Fermi, was thinking about it over lunch and then sort of stopped talking for about 10 minutes while he thought about it, then kind of came to and said, where is everybody?
Yeah.
And
it's almost impossible that they don't exist.
That's right. So, but where are they?
Yeah.
And that's the challenge. It's like, well, put some numbers on it. They should be everywhere.
Yeah.
Earth should have been visited many, many times, and we should have seen a lot of evidence. There's something, and that's why it's a paradox. Something in that prediction of those numbers doesn't make sense either.
It's not in actuality happening.
It didn't. Maybe the chances of intelligent life, there's a step there that's very unlikely. Possible.
Something that we're just miscalculating.
Exactly.
Yeah.
Maybe they're everywhere, but they're just so far away. Maybe we're the first in terms of. Maybe they're not observable.
Yeah.
Maybe we're not looking. I got a shock when I was actually, it's funny, I was having lunch with years ago with a key person who was driving SETI, Search for Extraterrestrial Intelligence, and I said, so how far out from Earth are we listening with SETI? And I can't remember the number, but it was not very far. The idea that at the moment these radio telescopes and other approaches at SETI, if you've seen the movie Contact, for instance, we're not listening to very far out at the moment. So it's probably not unreasonable that we haven't heard anything.
True.
And
how far are we listening?
I don't know what the number is, but it's in the radio domain it's not particularly far. It's moving into optical means of listening now. But space is just, the universe is just so large. That's the challenge. Just there may well be intelligent life, but they're so far away. Trying to contact them, try to interact with them, I think is the big challenge.
You remember that signal once? I forgot what it was called. There was one time some signal, and it was what they say is it was without a doubt an intelligent signal. It just didn't sit in with any other signal that comes from it. When was that signal? Is that something they captured in the 80s or something? They captured one signal one time from outer space.
I think there's a bunch of those where they don't repeat. So it could be a noise processor, or it could be some.
Oh, really?
Some no one knows. Or it could be life. Recently, a few years back, it was observed that there was, an object moving through the solar system on a trajectory that can't come from within our solar system. And either it's a runaway, asteroid or something from a different solar system, from a different star system that's been flung out, and it's cutting across a trajectory that it's obviously from somewhere deep out there, interstellar object. Or it could be, the idea was floated. Maybe it's a space probe. And the crazy thing
they just put out a million videos of space probes and stuff, just all of a sudden, like 3 years ago, like, what was it, 40 years? They said, nah, there's nothing. And then like 3 years ago, they go, here's like 50 videos of UFOs. We don't know what they are, but you all right. There's like little balls flying around and chasing
a lot of open
questions. And stuff.
Yeah.
Let me ask you something about astrophysics, bro. Like, I always had this one question, right? It's about the moon. It's about the dark side of the moon. You know much about like astrophysics, the motions of...
A little bit.
This is one thing that I just cannot get my head around, all right? We only see one part of the moon.
Yeah.
There is a dark side of the moon that we don't observe.
Yeah.
And I just want to know, right? With any intelligent, logical mind out there, how the theory goes, the stationary, relatively, no, it's not even stationary, the sun, our perspective, stationary sun, and Earth revolving around at 300, once every 365 days.
Yeah.
As that Earth is spinning, right? Stay with me. As that Earth is spinning, you probably know where I'm going to get to because your mind obviously works good. The Earth is doing that every 24 hours. So you've got this ball that's flying around like this.
Yeah.
Then we have a moon that whilst that's doing that, and there's a tilt for the season, there is also the moon, which is going around the Earth. And in all of those different enormous planes of motions and speeds, that the moon never ever tilts 1 degree and we ever see the other side of the moon. How is that possible? How is the moon just so locked in all of that motion?
Yeah.
Is that really the theory they give us, or I have some misunderstanding?
No, you've got it.
Why it hasn't shifted to we observe a single new part? Like, how is that even possible?
I mean, it's in a very stable orbit. So we're looking at what you'd call the dynamics of that system.
Yeah.
4.5 billion years after it was created. So in the early times, you probably saw a lot of crazy motion until it settled into a very stable state. Right. It's gravity locked. So the face, the rotation of the moon, there is no rotation of the moon with respect to the Earth's face there. But it's crazy to think of that. And then the solar system is also moving at some incredible speed.
And the arm
of the galaxy.
It's just right. Every single thing is moving at uncalculable speeds except this moon. It's just locked onto us like a magnet, staring at us with its asteroid holes.
Think of where we were in space an hour ago and how far we've come. You've left that world behind.
True. But can you give us a 101 here? String theory, what you know about it?
Yeah, it's a really advanced topic. It's an area of, I would say, particle physics, where trying to really understand the underlying fundamental aspects of particles like electrons and the fundamental particles.
Sort of like the Hadron Collider stuff?
Absolutely. So within that kind of branch of physics, it's a mathematical theory for how particle physics emerges. Now, I say mathematical because at the moment there are no experiments that can test string theory. And it's not clear how you would ever do an experiment to test string theory, the energy you would need to get to that regime. So a lot of people will tell you, well, it's not really a science. You can call it a mathematics, but there's no means of testing whether it's right or wrong. It's it remains a theoretical construct, but it's effectively, you can think of it as some sort of vibrational mode, and depending on the character of that vibration, then certain particles are associated with that vibration. At the moment, I mean, it operates in higher dimensions than 3 dimensions. So, and there's different classes of string theory. It's trying to unify gravity and relativity, so special relativity, general relativity, time dilation, all of that stuff, with quantum physics. At the moment, we don't really have a handle on how to connect these worlds. They're separate areas of physics. String theory very elegantly unifies gravity and quantum physics in a lot of ways, but it's still sort of out of the realm of testability. But it's an open area of research at the moment.
But I've got this quote here. Albert Einstein once taken issue with quantum physics. He said, what's the quote? God does not play dice. Do you ever feel like, it's sort of like what I asked before about, like, what do you see the dangers are with that? What do you think he meant by that? Have you heard of that quote?
Oh, absolutely. It's one of the fundamental ones. He's getting at the nature of quantum physics is that it's, I'm trying to avoid technical words here. So I would call it stochastic or randomness. And as humans, we really struggle with that. The idea that an event would happen or something would take place randomly that wasn't caused by some previous event. So quantum physics breaks that causality. We think event A happens because before it, some other event happened, and that led to that. And that event leads to something else. And over time, all events and all things are connected. in terms of causality. And when you're talking about quantum physics, this God doesn't play with dice, is that there is a truly random outcome in an event. It's not determined by, as far as we can tell, it's not determined by some other uncovered factor. So I'll put it this way:
it must put a lot of fear
in a way. It has. I mean, if you think I'm going to toss a coin, and we will say, well, the outcome's random. Well, no, not really.
If you have the means of measuring
exactly,
it, you will know.
Exactly. It's just that those means are hidden from us.
Yeah.
If you knew the mass, the angle, the air, the temperature.
But what if it really was random? Yeah.
In quantum physics, it's random.
He sounded when he said that like an element of fear.
In some ways, a lot of people have written about the philosophy of that. It opens, and I mean, this is a very interesting sort of topic. It opens a means by which, a godlike entity can manipulate certain outcomes without violating the rules of physics. Yeah. So, if otherwise we're just a clock, wind us up.
That is very interesting.
And we just run through and just play out the things that... Where's free will in a universe where everything is determined? Mm-hmm. So if you've got a problem with that, if you think humans have free will, when I decide to do something, I decide it. It wasn't simply just that the atoms in my body are obeying the laws of physics and I'm just, what am I? If you want to believe in free will, this opens a door to free will. Yeah. That those random outcomes... They aren't predetermined. They don't connect to previous events. Where do they come from? We don't know.
So wait, is it already known that there is random outcomes?
Absolutely.
It is known now. Yeah. And how long has that been known for? Not long.
Since the beginnings of quantum mechanics, so about 100 years ago. Yeah. And you can go to a lab, the lab down here, do an experiment where you see that randomness. Yeah. Those fundamental particles, you cannot predict, is it this or is it that?
I would think that I could be completely wrong here, but knowing that would have opened up a scientist's mind and science in general's attitude towards an intelligence beyond ours, an intelligence to the universe. Yeah. In a different way, if some people might call it a god. Because I can imagine 150 years ago when they didn't think there was a randomness out there, where everything was a mathematical equation, there's nothing more to it. Yep. It completely would rule out your mind for, no, there's nothing behind anything, everything is just this trajectory and I can tell you everything about the world. But to come to face a situation like that, well, wait a minute, there's something else there that's going to make it impossible for us to ever know everything. And there must be something else behind that, because the randomness, is it really just random or is there something behind that?
Changes that view of, you could say there's a god that's a watchmaker and put the watch together, wound it up, and let it go, and then took off. It's set. And we're just moving through the motion of that. That was, as you say, in some ways the physics and the philosophy of at least what physics was telling us pre-quantum mechanics. Yep. Quantum mechanics comes in 100 years ago and says, well, actually, the measurement outcome or what happens at one point in time is not caused by what happened the second before. Yeah. In fact, it's just completely random. Yeah. And you can't determine it. Okay, but there are still rules. It's not like it's just chaos and not, the probability is still there, but the exact outcome you can't say. You can only talk within statistical probabilities. That opens the door for human free will and opens the door for an entity like a godlike entity that can skew and manipulate individual outcomes.
And it definitely holds us back from knowing every single thing then.
Yeah, absolutely.
So it's like all the scientists, physicists / astronomers and all saying the same thing of like the Renaissance. They were just thinking of things that were not known, not just calculating the known.
Yeah.
It's like we live, would you say, nowadays, maybe even so more. The Renaissance is a great time. But I would say that the developments we're having in the last maybe 80 years, maybe I'm completely wrong, blow those out the water.
It's accelerating.
It's going crazy. It's accelerating, Like what's happening in the last 80 years, we really live in, I feel like we really live in a time that will be looked back on as like the people of this generations were like.
Yeah. I
wonder
completely
what
agree.
it is. I wonder if it's like something that we're doing. Is it, or is it just the natural process, and that's where we're at in technology and understanding that it was always going to happen? It's like, you know how they always think like at a certain time they look back and it's like maybe the Renaissance happened because of the introduction of caffeine, and maybe we the monkeys started eating because of the, you know what I mean? I wonder if they look back and it's like it's because you know what I mean?
Some areas it's accelerating, you know, it's growing exponentially. More and more people are working on scientific and engineering technical areas. So that's advancing. There's more money that's driving and more economic factors are driving. But it's not universal. You have to be a little bit careful because there's a school of thought, you can read books about, you know, the singularity, where we're just accelerating in our knowledge and AI and then all of a sudden, you know, there's just going to be some switching on of some AI that's going to, you know, have to be a bit careful. There are things like flying across, let's say, the Pacific. It took roughly the same time to cross the ocean in a commercial jet today as it did 10 years ago, 20 years ago, 30 years ago. So why is that? Well, planes can go faster, but we don't need them to go faster, or there's other reasons, not economic to go faster. And so it depends. But in certain areas of science, as our understanding grows and more people are pursuing that, there's a huge advancement. The world it's going to get exciting. A lot of people, particularly young people, sometimes have a romance of the past, which I totally get. You know, if you ask the question, where would you like to be in time if there was a time machine, where would you go back and what would you want to witness in history? And a lot of people say, I'd love to be there at the invention of some piece of technology, or when they first understood the transistor, or they first invented whatever.
Probably be actually pretty uneventful at the
pretty
time.
Uneventful. Or when Einstein invented relativity, you know, and it's a romance that there were these big breakthroughs and now everything is known. And yet we're living right now, particularly like this year, next year, right now, at a point in time where equations and mathematical symbols written on a piece of paper are coming to life. We're doing experiments to prove out that indeed that math describes reality. And now we're starting to build technology. And there's this story, this kind of narrative that goes from understanding the mathematics, testing it out, and then building stuff with it. From Industrial Revolution, you know, steam engines and so on, that comes from thermodynamics and understanding the equations of thermodynamics. Radio, television, wireless. I mean, why did it appear when it did? Well, because in 1850, Maxwell wrote down the equations of light and of radio waves, which are a form of light, unifying magnetism and electricity. So once that mathematics happens, the understanding is there, and then the technology follows. We're living in an era where we've got these equations of quantum physics. We're starting to show that those equations are real, they describe reality, and now we're starting to build technologies from them. And in our lifetime, I mean, I think it's just amazing to see it go from math on a paper through to something you're going to hold in your hand effectively and use to do, you know, your daily life, and watch that transition over the next 10 years.
Give me, before we go, give me a projection, a realistic projection of how you see this. How you think this will come to affect our lives in our lifetime? Do you think this will we see this in our lifetime? What do you imagine?
Yeah, I mean, we'll see. There's no question we will see that transition, and it'll be like everything, almost unnoticeable in the moment until you look back. What I can't do, or can't do very well, is name the application. What is it going to be for? And it's. I've been reading a lot about this recently, I get the question, what's a quantum computer good for? You know, and you can give examples. Well, we know you can write codes with it. Okay, whatever that's good for. We think it's going to be useful for solving chemical problems and finding certain pharmaceuticals and materials, probably. Then, you know, there's other applications, but it's getting thin.
And it could be something completely different. And probably will be.
If you read, like of the history of, say, the transistor or the first integrated circuits, the first computers, there were interviews done with people who were building it out and what's it good for?
Or even discovering radiation.
Absolutely.
What's that woman that's discovered the first radio?
Marie Curie.
Marie Curie. And it's like asking her, well, what's that good for? She's going to be, I don't know, I just discovered it.
Exactly.
You deal with it.
First transistors, they thought, well, it's small, it might be good for a hearing aid.
Yeah.
They didn't envisage playing, games. They didn't envisage like Instagram that would emerge when you had billions of those things wired up together. And that's, it's not that long. That's 40, 50 years from the very first element to billions of transistors wired together where we're now running, very complex software and we're using it to entertain ourselves. Very short time. So we're at that point at the moment, we're just switching on in terms of quantum computing, the very first equivalent of the transistor. But I think very quickly that will take off. And it's really hard to see where that lands. The physics is different. It's going to be impactful. There's no question about that.
I wonder if someone's going to just full hog the technology. I wonder if
I hope not.
Yeah, I wonder if it's going to be like that, because it's powerful. I wonder if someone's just going to get it. That's ours. Like how they are with nuclear technology, how they try not to let everyone have it and it sneaks out and Pakistan has it. I wonder if they're going to be like that. Some super company like Microsoft will just be like the bosses of the world with their nanotechnology.
Well, it is. Maybe, it's a concern that the geopolitics is a concern. There's no question of that. But ideally companies like Microsoft that, like AI, have already ethical frameworks and government involvement and the structure around it, so you can't just go randomly off and do whatever you want. They're going to be critically important, no question. These ideas can't be the domain of people that are in only certain areas of society. And I would love it for, as you say, people in this area, Glebe area, Matraville area, whatever. If they're interested, follow that interest. And, you can be at the forefront of that stuff, involved in those ideas, doing it every day. It's not to say that it's easy and not to say that I obviously didn't, I'm privileged in a lot of ways, doors open for whatever, but, and that's not everybody has that kind of option. I get that. But at the same time, if there's something that in my story gives people a vision of in little old Australia in the back end of Sydney, it can be done, and it's happening 100%. Right here, and we want to, we should be talking about these interesting things more and more.
I 100% agree with you. I heard I got an invite. To the
absolutely.
I'd love to do that.
Come have a look.
We'll come down. I'll make a little video about it, and you can show all the boys what's going on there.
Exactly.
It's
visually very interesting to see.
I can imagine it.
Crazy equipment.
I can imagine it. That's what my manager was saying, that you want me to come down and see what you do and all that stuff. I'm gonna be sick. We'll get that done.
Let's do that.
100%. Thank you, brother. Thank you for coming on.
Thank you.
Mad conversation. Thank you.